Alright guys, we're going to go over the harmonic motion FRQs that I assigned last week. In just a moment. Gonna let some people come into the stream here. So we'll get started in just a second. Maybe I'll stream Warzone after this. I'll think about it. I will think about it. Hello. It reminds me of a song. Yeah, there's no amount of training that you could do, David, to allow you to come anywhere close to my level. I proved it in Warzone. I proved it in Teamfight Tactics. Well, just stop. Just stop embarrassing yourself. All right, I'm gonna wait another minute and a half, then get started. Let some people, whoever else is gonna come watch this, come watch. All right. Okay, let's get started. Those of you people who aren't in the stream can watch the video later. So we had 2 FRQs to do last week over simple harmonic motion. Here's the first one. We've got a 20 kilogram box on a horizontal frictionless surface. So just draw a little picture real fast. We got a frictionless surface. We got a 20 kilogram box. And it's going to collide with a spring. It's going to move to the right with a speed of 4 meters a second. I like Twitch because you can see this chat in the OBS, but you can't do that with YouTube. All right, so 4 meters a second to the right, the box hits and remains attached to one end of a spring of negligible mass, whose other end is attached to a wall. All right, so here's the wall. And there's a spring attached to this guy, and the box is going to collide with the spring. As a result, the spring compresses to a maximum distance of 0.5 meters. All right, so eventually the spring will compress to say, I draw this better, I guess, but so spring is going to compress to here. So from its original position to there, right? 0.5 meters. That's a little small, but hopefully you can see it okay. And the box is here. All right, you get the idea. And the box then oscillates back and forth. All right, the spring does work on the box from the moment the box first hits the spring to the moment the spring first reaches its maximum compression. Indicate whether the work done by the spring is positive, negative, or zero. All right, well, hopefully you all recognize that this one answer should be fairly clear. The answer is negative. You can do negative work. Justify your answer. Again, how many points do you think you earn for clicking or for checking off negative? 0 points. You must justify it correctly. There are, I guess, 2 ways to think about the justification here. Remember that the equation for work, or one of the equations for work, is force times displacement. Well, what is the direction of the displacement? Well, the box is displacing from left to right, right? So it's going in this direction. What is the direction of the force on the box? It's the other direction, right? It's going from right to left. The spring is pushing it the other way. So they're opposite directions. If they're opposite directions, then we must have negative work, right? It's going to be negative because we have, say, positive displacement and negative force, or vice versa. Either way, they're opposite, so you get negative work. The other way to think about this, and the way that I kind of like thinking about it better, is work is also the change in energy, the change in kinetic energy, right? Well, this box starts off moving. It's got a velocity of 4 meters a second. And then after that, it has a velocity of 0, because once the spring fully compresses, the box stops for a moment. If the box is slowing down, that means we have final minus initial. Our final kinetic energy is going to be let me erase this. Work. Our final kinetic energy was 0. Our initial kinetic energy is some value, right? We had something in the beginning. We don't know what it was, right? Some number. I say it's 10. I don't know what it is, but we'll figure it out. Well, 0 minus anything is going to be a negative number, right? So we're going to have a negative number there. I just made up 10, but you get the idea. It's going to have negative. And I think about it, remember in class I mentioned this before. If we're taking energy away from something, that's negative work. So the box is slowing down. Therefore, we are taking away, the spring is taking away energy from the box. Therefore, it's negative work. Also, the force and displacement are opposite directions, so negative work. Calculate the magnitude of the work described in part 1. All right, well, so here, we're going to calculate it. All right, yeah, so like I just said, the magnitude of the work done described in part 1, right? Sorry, I was looking at my other. I just keep getting a warning from YouTube saying my bitrate is too low, but I don't know what that means, so whatever. Right, okay, so we know that work, the equation I just used here is what I'm going to use in part II. So work, there we go, equals a change in kinetic energy, right? So work energy theorem. Well, we know that by the time that the box fully compresses the spring, the velocity of the box is 0, right? The box collides with the spring, it slows down, and then it stops for an instant, and then before it bounces back, right? And it's asking us how much work the spring does to stop the box. It says the spring does work on the box from the moment the box first hits the spring to the moment the spring first reaches its maximum compression. When the box meets its maximum compression, that's when the box has no velocity because it's fully compressed, right? All the energy is now in the spring potential energy. So our velocity is 0 of the box. So we're going to have work equals kinetic energy initial, or sorry, final minus initial, excuse me. Final minus kinetic energy initial. We know our final kinetic energy is 0 because the box comes to a rest, minus my initial kinetic energy, which is 1/2 mv squared. Plug in our numbers, 0 minus 1/2. The mass of the box was 20. My initial speed was 4. That's being squared. So let's see what I'll do. I'll get my calculator out that I got downloaded the other day. Somewhere. Where I put that thing? Wabbit. There we go. And so we're going to do 4 squared times 20 divided by 2, and I get 16 joules. Is that right? Wait. 4, did I do times 2? Times 20. Okay, I did times 2 instead of by 20. 160. Okay, that's, I was like, 16 is not right. Okay. Yeah, 160 joules of energy that the spring takes away. It should be negative, right? It should be negative energy there. The work is negative. Make sure you want to include that negative sign because it is negative energy or negative work. All right. So that's part A. Now go to part B. Calculate the spring constant of the spring. Check for questions. All right. Now that we know how much work was done, we know how much spring potential energy there is. Once the spring fully compresses, we know that. I'm going to go back up to my picture here. Let's call, when the spring is in this position, let's call this position 1. And when the spring is compressed at 1/2 meter, let's call that position 2. Right? So we know then that the spring potential energy at position 2 must equal the kinetic energy of the box at position 1, right? They have to be the same because the kinetic energy of the box is transferring itself into the spring energy of the spring, right? The box comes to a rest, but the spring gains potential energy. So those two energies have to be the same, right? Well, we know how much energy there is in kinetic energy there was. There's 150 joules kinetic energy, right? Because that's how much energy there was at this position here in the box as it was sliding towards the spring, right? And all that's going to turn into spring energy. So they're the same. The spring energy is the same as the kinetic energy before they collide. So instead of having U, I'm going to put in the equation for spring energy. 1/2 little k x squared. And I know what x is, right? Because we know that the maximum compression was 1/2 meter. So I get 160 equals 1/2 little k, spring constant, times 0.5 squared. And I'm going to solve for k. So again, I'll get my calculator here. 0.5 squared. It's 0.25, so you get 160 equals 1/2 little k times 0.25. Half of 0.25 is going to be 0.125, but I'll do it on here. So I get 160 equals little k times 0.125. I'll divide both sides by 0.125. And I'll get a little k of 1280. 1,280 newtons per meter. Everybody good with that? All right. Okay, cool. Let's go to part C. Calculate the magnitude of the maximum acceleration of the box. All right, well, we learned some formulas from the bookwork about how to find acceleration, although, to be honest, that formula was really irritating. Here's an easier way to do it. Newton's law still works. So acceleration, according to Newton's second law, is acceleration equals the net force on an object divided by its mass. Well, we know that at the spot we have the maximum acceleration should also be the spot we have maximum force, right? They're best friends. Acceleration and force best friends, so max acceleration equals max force. So where do we have the maximum force? We have maximum force when the box is at maximum compression, right? This is where Hooke's law is going to come into play. Remember, Hooke's law says a force of a spring equals to kx, where x is the displacement from equilibrium and k is the spring constant of the spring. Well, we just found the spring constant of the spring, and we know that x at maximum displacement is 0.5. So we should be able to find the maximum force, right, of the spring. Max force, S for spring right there. And that's going to be the spring constant 1280. Where is the maximum compression of the spring? It's at 0.5 meters. We found that earlier. So the maximum force is half of 1280, which is what? 640 newtons. So I got over here to my acceleration formula, and now I know, okay, well, the max force is 640 newtons. The mass of this thing was 20 kilograms, so that should mean max acceleration will be 640 over 20, which is 32. And there we go. All right. So the key here was recognizing that the spot where the maximum acceleration exists is the spot where the spring is the max compression, which is at 0.5 meters, and you know the spring constant, so you can find what the force is at that position, and then put it into Newton's second law. Okay. Thanks for the inspiration. All right, part D, calculate the frequency of the oscillation of the box. All right, well, we know that frequency is 1 over the period and all that. So I'm going to go ahead and find the I like finding period first. It's easier for my brain. So I know period of a spring oscillator is 2 pi times the square root of, is it m over k? M over k. I always forget if it's m over k or k over m. M over k. And then once I find the period, I can just do 1 over the period to get my frequency, right? So, and we already know m, we know k, we found it earlier. The mass of this block is 20 kilograms. And then the spring constant we found to be 1280. All right, so all that under the radical. And then I just punch in my calculator. So I'll put my calculator up. So I'm going to get 20 over 1280. I'm going to square root that number. Okay, and I'm going to do times 2 pi. All right, so that's my period. Now that's period, not frequency, right? That's a frequency. So 0.785. So period is 0.785. I'm going to invert that number now, right? So I'm going to go back to my calculator. 1 divided by that guy to get my actual 1.3. We'll call that 1.3. So my frequency then 1.3 hertz, right? Oscillations per second, 1.3. All right. Any questions so far, guys? Anything? We good? Just want to quote the great Jean-Luc. Okay, sounds good. All right, let's go to part E. It's the graphs. Let x equals 0 be the point where the box makes contact with the spring, with a positive x directed to the right. On the axis below, sketch the kinetic energy K of the oscillating box as a function of position x for the range negative 0.5 meters to x equals positive 0.5 meters. So this is where the spring makes contact with, or the box makes contact with the spring, right at the 0. So it's going to oscillate back and forth. It's going to go from negative to positive, and it's going to go back and forth, right? Back and forth. So we know we should have some points we know about here, right? We know that we should have the minimum, we should have 0 kinetic energy at the ends, right? Because the spring isn't moving, or sorry, the box isn't moving as a box. The box is not moving at the ends, right? Because the box oscillates to the left, slows down, stops at the maximum displacement, goes back, slows down, stops the maximum on this side, and it goes back and forth, right? So we know we should have no kinetic energy here or here because the box isn't moving at those positions. So nowhere at 0. And we should also be able to kind of ration out that the box should have maximum kinetic energy at the center, right? Because there is no spring energy there. So where's the energy? Well, then it's all in the spring in the form of kinetic energy. So you have maximum kinetic energy at the middle. Now the question is, how do you connect these? Do you connect them by straight lines? Is it just like a big triangle here like this? No, it is not. It should look like this. It's going to be a concave kind of curve. Something like that. Of course, hopefully yours is better looking than mine, but let me try that again here. Okay, it's a little better. All right, so why is it curved like that? All right, well, remember, guys, that your velocity, the spring energy, let's go that. Spring energy is 1/2 kx squared. Well, at this position here, right, we have maximum x, maximum displacement from the equilibrium. So we have all the energy in the spring. Now you might say that, say when we're here, this position right here, we've lost that much of our x, right? We've lost that much displacement. Let's call that x prime, all right? So how much kinetic energy do we have? Well, we have our kinetic energy then will be equal to the spring potential energy that we lost. How much spring potential did we lose? Well, we lost 1/2 little k x prime squared worth, right? So it's not linear because of this squared sign right here, right? It's not linear. We're actually gaining, it's going to go up like that because of the squared sign in the equation, right? I hope that makes sense. So the kinetic energy we gain is equal to the spring potential that we lose. And since the spring potential energy has that squared sign in it, it's not a linear relationship. It actually goes up really fast, kind of flattens out at the end, and then goes back down this same way on the side. All right, so hopefully that makes sense. All right, last graph here, graph 2. On the axis below, sketch the acceleration A of the oscillating box as a function of position x for the range -5.5 meters to +0.5 meters. All right, so similar one with this guy. You should be able to ration out that the acceleration is 0 at equilibrium position because there's no force. Remember, force of a spring is equal to little kx. Well, at equilibrium position, there is no, x is 0. There's no displacement, so there's no force. If there's no force, there's no acceleration. But the same token, you feel the rationale that at the negative position, we should have a maximum acceleration, and then also a maximum acceleration in the other direction here. All right, so why is it like that? And is it going to be like some kind of weird curve, or going to be a straight line? Let's think about it. At maximum, or ask yourself, what's the relationship here between my position and my force? It's linear, right? It's direct. So therefore, we're going to have a straight line from here all the way down. Something like that, right? All right, so why is the acceleration positive when our force or when our displacement is negative? Well, again, think about which way the force is. When you have your spring, and let's say equilibrium position is here, if my spring is compressed all the way to the right, like this, in this direction, then the force is then this way. So my displacement is positive, right? Displacement x positive here to the right, but the force I'm pushing back with is negative. If the force is negative, the acceleration will be negative too, right? That's why when I have positive displacement, I have a negative acceleration. When I have negative displacement, so when the spring is all the way out here, stretched out, right? The spring is pulling it back this way. The force is to the right, positive force, when I have negative x displacement. So they're flipped, right? So it needs to be like this. If you drew it like this, that's wrong. That's incorrect. It needs to be like this, top left, down to the bottom right. Okay? linear relationship between my force and my displacement. If there's a linear relationship between the force and displacement, there's also a linear relationship between acceleration and displacement, because force and acceleration are directly related to each other. All right. All right. Okay, hope that makes sense. I don't see any questions in chat. All I see is Jean-Luc Picard quotes, and that's about it. So I guess this is making sense. If you're watching this later and not during the stream, just as usual, message me on Remind or email me if you have any questions. Okay, let's go to the second FRQ we did. This one had a pendulum on it. A pendulum consists of a bob of mass 0.085 kilograms attached to a string, a length 1.5 meters. The pendulum is raised to a point Q, which is 0.08 meters above its lowest position, and released so that it oscillates with a small amplitude theta between the points P and Q as shown below. Okay. A, on the figures below, draw a free body diagram showing and labeling the forces acting on the bob in each of the situations described. When it is at point P, all right, when it's at point P, what does the free body diagram look like? Okay, well, it should be fairly straightforward here. I'm just going to simply draw the tension this way and the weight of the bob down, mg. And there you go, that's it. When it's at its lowest position, I'm going to have tension straight up and mg down. Looking at the rubric, I don't think they care too much about how long the air, I mean, they need to be relatively consistent. The tension up here should be a little bit larger, technically longer than the arrow down, because you have centripetal acceleration up towards the center of the circle. But and this one should be longer, but they don't seem to be too nitpicky about it. As long as you draw the arrows correctly labeled in the correct direction with a reasonable magnitude, look like you're good. All right, calculate the speed of the bob. The speed, I don't know why they say u of the speed, but they're saying u for speed for whatever reason. Calculate the speed of the bob at its lowest position. All right. We had problems like this from our before. Wait, but isn't 0 the point where the spring? Yes, David, it is. Okay, let me go back. Someone asked a question. The chat is pretty laggy behind where I am at. So, what was your? Isn't 0 the point where the box hits the spring? Yes, that is the position where the box hits the spring. Why does that matter? Are you talking about the acceleration graph or the kinetic energy graph? See, there's another reason why I don't like YouTube. I gotta sit here and like wait for the chat to catch up, because there's like a really long delay. All right, well, ask your question, David, in the chat, and then I'll get to it. The 0 is the equilibrium position of the spring. Okay. Should be going to the origin here. I mean, I can't. Why is it so hard for me to like the most inept artist of all time? Whatever. I guess I could do like a. Dang it, that didn't go through the center either. All right. Oh, David, I don't understand. Yes, the origin is the position, is the, is the equilibrium position of the spring. What's your point? I'll go ask your question in chat, and then I'll get back to it. Right, so back to part B of the pendulum, calculate the speed u of the bob at its lowest position. Okay, well again, we know that at its lowest position, it's going to have 0 potential energy. Again, let's call this position here, and when it's at its lowest position, let's call it position Z. So we have position Q and P at the top and position Z. So we know that the spring potential energy of the pendulum bob at position Q must equal the the kinetic energy of the pendulum bob at position Z, right? They must be the same because at the highest position, when all the energy is in gravitational potential energy, I said spring, I'm going to say potential gravitational, should be G here, sorry about that, G. Gravitational potential energy at the highest position, as it swings down, right, it loses potential energy, but it gains kinetic energy. At its lowest position, it has no potential energy, it's all in kinetic. So we know they must be equal to each other, these two energies at these two positions. So what kind of energy do we have at position Q? It's mgh, the height, how high we are, and it equals 1/2 mv squared. The m's will cancel, you'll notice, right? We're going to get g, which is 10, times h, the height was 0.08 meters, equals 1/2 v squared. 10 times 0.08 is 0.8. Can you only even see this on the... Or am I too low? There you go, okay. Let me go up a little bit more. That's easier to see. So 10 times 0.08 is 0.8 equals 1/2 v squared. Times to both sides, I get 1.6 equals v squared. I square both sides, and I get a velocity of... Turn this guy back on. Oops. Square root of 1.6. What's happening here? Okay. Square root 1.6. 1.26. So let's call it 1.3. We get a velocity of about 1.3. Oh, they wanted to call it u. I don't know why, but whatever. My u's always look like ins or... There we go, u. All right. Okay. Hope that's good. David's still thinking about the other problem, but that's okay. Just ask in chat whenever you know you're asking there. Calculate the tension in the string when the bob is passing through the lowest position. All right, tension in the string in lowest position. Okay, so for this one, a little tricky. A lot of y'all were asking about this, and I tried to give you hints, but I don't think y'all quite got there. We know that net force equals mass times acceleration, right? We know the forces on the at the lowest position are right here, right? This is our free body diagram at the lowest position. We have tension minus mg equals ma. Now, what kind of acceleration is this pendulum bob experiencing as it passes at lowest position? Ask yourself that real quick. Answer in your head. What kind of acceleration? Does it have any acceleration as it passes through this lowest position right here? Think about the motion it's making, right? It's going from point Q down here, to here, back up to here. If we were to imagine that this pendulum bob kept going all the way around, wouldn't that be circular motion? So doesn't it have centripetal acceleration towards the center of the circle at this position? And the equation for centripetal acceleration is v squared. I cannot write. It's so frustrating. V squared over r. So the acceleration we have here is centripetal acceleration. So we're going to say tension in the rope minus mg equals m times v squared over r, because we're experiencing centripetal acceleration as we go around the loop. Even though we're not making a complete circle, right? Remember, we mentioned this before in class. You don't have to make a complete circle to be experiencing circular motion. When you go over a hill on the road, or you make a right-hand or left-hand turn, even though you're not making a complete circle, you're still experiencing circular motion while you're in the curve, right? Same thing here. We're still experiencing circular motion as we go through that part of the pendulum swing, right? All right, so I'm going to get tension equals, I'm going to add mg over to this side. And I want to get mg plus m, should be minus or, yeah, plus mv squared over r. I'm going to factor out an m here, so I'm going to get tension equals m times g plus mv squared over r. Oh, whoops, I just said factor the amount. I didn't do it. I'm dumb. Sorry. G plus v squared over r. Like so, and I'm going to calculate, plug in my numbers, so I know the mass of the pendulum bob was, what was it? Very small, right? 0.085. So this is 0.085 times g's 10 plus my velocity, which I found before in part B to be 1.3 squared over the radius. The length of the string was 1.5 meters, right? So that's 1.5 r, right? If the length of the string is 1.5 meters, that means you make a complete circle, the radius is the length of the string. And we're going to plug in our equation into our calculator and find our tension. So I'll get the calculator up. All right, so 1.3 squared divided by 1.5 plus 10. Plus 9, I guess. And then times the mass, 0.085. And I get about 0.94. Let's call it 0.95. So 0.95 newtons. Which again makes sense, right? It should be just larger than the weight of the pendulum bob, because the weight of the pendulum bob is going to be 0.85. So that makes sense the tension force is a little bit more. Otherwise, it wouldn't go in a circle, right? If the tension force was equal to the weight force, then it wouldn't accelerate at all. It would have no net force, it would be 0, and it would go in a straight line. It wouldn't curve. It has to be up a little bit, the net force, to make it go in a circle, right? That's centripetal force to make it turn, make it go around in a circle. All right? And the last part, we're almost done. Part D, describe one modification that could be made to double the period of oscillation. All right, there's really only one. Technically, there's two things you could do, but one of them is really, really hard. So let's look at the formula for period. Period is T equals 2 pi and the square root of L over G, or is it G over L? God, I always forget. I always forget this. I'm pretty sure it's L over G, right? Yeah, L over G. Okay, what can we do to make the period twice as long? Think about it for a minute. Think about it. Look at our formula. What's the relationship between L and the period T? L and T. What's the relationship? It's a root relationship, right? We have T is what's the little symbol for? Is proportional to the square root of L, right? If nothing else changes, if G is the same, and of course pi is a constant, 2 is a constant, if G doesn't change, acceleration of gravity, then if only L is changing, then we can say that T is proportional to, that's what the symbol right here means, proportional to the square root of L. Well, if we want the period to double, well, we can't double L, because then T would go up by the square root of 2. But what if we made L 4 times bigger? So T is proportional to square root of 4. Square root of 4 is 2, right? So that would make our period 2 times bigger, right? It's the worst symbol of all time. Try that again. There we go. Period will be double then, right? If we increase the length of the pendulum by 4 times longer. There's one other thing you could do, but it's really hard. You have to go to a different planet or something like that, or go like really far away from the Earth. You could say period is also proportional to the inverse root of G, right? If, again, 2 pi doesn't change, L doesn't change, if we change it to G instead, then we could say that if we lower G by 4 times, right? We made G 1/4 of what, 0.25? Then doesn't 1 over 0.25 also square root of 4, which is equal to 2? So we could either quadruple the length of the string, 4 times longer, or we could make gravity somehow magically be 1/4 as strong. That's harder to do, but you get the idea. That's what you could do those things. All right. Okay, so that's it for the FRQ from Harmonic Motion. You have 4 more problems you're working on. These ones are going to be due spaced out throughout the week, so make sure you read the syllabus and keep up with your work. Don't procrastinate. That's all I got. So I'm going to wait like 10 seconds here for any other final questions from chat over these harmonic motion problems. Let chat catch up to my live self here. If you have any questions watching these, just message me on Remind or email me. Remember, guys, you can always do the video chat, like a one-on-one through Google Hangouts. That's totally fine with me. If you want to do something like that, so just let me know if you want to, if you need to. All right. People are logging off. All right, fine, whatever. Okay. David, you never asked me about the other problem, so I guess you figured it out. Oh, now I see your question. Why does it? Let me go back real fast. There's no change before. This is not it's not time on the x-axis. This is position. There's no before. This is just as it oscillates back and forth. As the spring oscillates from equilibrium position to here and back and back. It's just saying it's not time on the x-axis. This is position. So when we're at position 0, there's no acceleration. When we're at maximum positive displacement, we have maximum negative acceleration. When we're at maximum negative displacement, we have maximum positive acceleration. This is not time on the x-axis. Does that make sense? There is no before on this graph. They're not graphing time. There's no time. Time is not represented on this graph at all. It's only position and acceleration. Good? All right, I guess you're good. Okay. Okay. All right, guys. Thanks for watching. Again, questions, email me. Remind anytime. We can always catch up on Google Hangouts, video chat. Stay safe, stay clean, wash your hands, don't touch your face, practice social distancing. Hopefully I'll see you again before the end of the year.